is Dr. D. Govardhan, Professor and Head, Department of Aeronautical Engineering, Institute of Aeronautical Engineering, Hyderabad. Today we are discussing theory of simple bending, assumptions, derivation of bending equations in the mechanics of solids. Now earlier we considered different types of beams such as cantilever beam, simple supported beam and overhanging beams. When they are subjected to point loads, it is also called concentrated load, uniformly distributed load and gradually varying load. When a beam is loaded, we identify the sections, how the shear force is distributing along its length, as well as the bending moments. When the bending moment is developing, the beam is always deflects from its original position. Sometimes we can say it is the action of the external loads. The bending moment at any section will always tends to bend or deflect the beam. The magnitude of deflection, it depends upon the magnitude of the forces which are acting, the elasticity of the beam, length of the beam and cross section of the beam. But here when the deflection is taking place, the internal stresses are developed, internal forces are developed in the beam such that it always oppose the deflection of beam further now. So at some stage, the effect of forces which are acting, which are creating the here bending moment, it is balanced by that internal stresses developed within the beam now. The internal stresses which are developed in the beam is also called the resistance stresses offered by the beam to the deflection. This resistance which is offered is called now bending stresses, and the relevant theory which is giving explanations of bending is called theory of simple bending. The following assumptions are made in the theory of simple bending. The first one is the material of the beam is perfectly homogeneous regarding its distribution of alloys as well as the physical dimensions of the same kind throughout, and isotropic, that is the elastic properties, that is the Young's modulus, bulk modulus and modulus of rigidity, all are equal in all directions of the beam. Generally the word is the material of the beam is perfectly homogeneous and isotropic. The material of the beam is tested within the elastic limit. That means after removal of the forces which are acting the beam regain its original shape or the original position. The transverse, third one, the transverse sections which are plane before the bending remains the plane after the bending also. That means if the beam is there here now, these are called transverse sections. Depending on type of the beam, it may be the square or rectangle or circular cross section. The cross section is which is there earlier now, having also the same now without deformations after the bending also. That means the transverse sections which are planes before the bending remains the planes after the bending also. The fourth one, each layer of the beam is free to expand or contract independently of layer above or below it now. Because here now, if you take the beam now, it consists of so many number of layers. When the force is acting on it now, just it deflects in the form of U shape as you know. That is all the layers which are there now in longitudinal directions now. All are free to contract or to expand when the bending process is taking place. The fifth one, the value of E, that is Young's modulus, it is also called modulus of elasticity, is the same in the tension as well as the compression. Sixth one, the beam is in equilibrium, that is, there is no resultant to pull or push in the beam section. So these are the assumptions made to explain the theory of simple bending. Simple bending. A theory of simple bending. In theory of simple bending, consider a small length of the simple supported beam subject to a bending moment as shown in figure. Here simple supported beam means the beam which is having support at its end position now. That means it is the beam is there having its supports like this. The beam is subjected to certain loads now. The load, it may be the uniformly graduate, uniformly distributed load, uniformly varying load, or it may be the point load. This I am taking here a point load less. Because of the effect of this force, the beam is deflected in the form of like this. This is called here sagging effect, or the concavity, the center of its concavity is at its top position. That is in the form. So here we are considering small portion of the simple supported beam. So the curvature of the beam is in this length is taken to be approximately a circular. Here we are taking this nothing but here now ABCD is representing ABCD is representing small portion of the simple supported beam when it is subjected to the bending moment. A little consideration will show that here in this case now, when I am taking now, it is a bender like this now. Here we are taking just a lines now. At the top it is represented AC. In the middle RS we are taken. At the bottom position CAB. So we consider the section between here AB as well as the CD and so on. But it is now bend in the form of curvature like this now. That is in the form of like this there now. There. This is nothing but the middle point RS there now. Now if you observe that AC, A dash, C dash is there now, that section, that layer, upper layer of the beam now, it decreases its length now. That is a contraction is taking place or compressive stresses are developed in it now. Now it is the earlier length is AC, it is compressed through A dash, C dash as shown in figure. When top to bottom, just when you are moving in downward directions now, maybe the curvature is there now. At some point to here RS is there now. At which the length of the beam it is remains constant. Or in other words, RS is equal to R dash S dash. And moving further now, at the toward the bottom of the beam now, the length of the beam is increases to B dash D dash. That is originally it is having BD and increased to B dash D dash now. That means here now the layer into R dash S dash the beam is not at all undergoing any compression or expansion, but above the R dash S dash, when you are moving upward direction, so the compression of the beam is increases, having this maximum at upper layer. Similarly, on moving in downward directions from R dash and S dash, the length of the beam there is also increases and having maximum at the bottom layer, that is at B dash and D dash now. So it is concluded that now the layer above have been compressed maximum, and the layer below the RS having this stretched, that means the extension is taking place. The layer RS is neither compressed nor stretched now. Hence, this layer is called neutral layer, or the plane which is passing through it, it is called neutral plane now. This is the theory of bending. It is also called theory of simple bending. Bending stresses. Again, considering this same figure earlier now, it is a part of the simple supported beam when it is subjected to load as shown in figure. Here we are considering here dx, it is before deflection is taking place or when there is no load is acting on the beam. Identified three types of layers. One is the AC at the top, RS the middle, and the B dot D at the bottom position now. When it is subjected to forces now, it deflects in the form of concavity at the top, or it is also called sagging effect. So in this case, on moving from R dash to S dash, R dash S dash, after bending we are representing RS by R dash S dash, and A dash AC represented as A dash C dash, and the B D original figure is represented with B dash D dash. So if you observe from R dash S dash, the length of the beam is remains constant. It is not at all undergoing any compression or tension. Hence, this layer is called here neutral layer. It is also called neutral plane now. So from neutral planes, as we are moving toward the top position, that is toward the AC, compression is taking place, and moving in downward directions from R dash S dash, that is a stretching of the beam or elongation of beam is taking place now. Now we are considering a portion, so P dash Q dash portion at a distance of y from the neutral axis as shown in figure now. This distance is equal to here now, here y position now. That is neutral position now. Now let this layer be compressed to P dash Q dash, just after bending as shown in the figure now. The decreasing length of this layer P dash Q dash because of bending moment is given by, we are taking delta L, which is equal to, since it is now above the neutral layer, the compression is taking place. That means the length of the layer is decreasing, and so change in length is equal to, that is it is equal to original length is equal to, we are taking PQ, this is before bending, to P dash and Q dash now. But if PQ is also equal to, we can write it to AC, or it is also equal to RS, or it is also equal to BD as shown in figure now. So strain is equal to, general word, it is defined as the change in length to its original length. So change in length is equal to PQ minus P dash Q dash divided by the PQ now. Now from this geometry of this figure now, here now, this figure now, if we observe, here R is the radius of curvature of the beam now, and y is the distance from the distance of p dash q dash layer from the neutral axis are taken now. Okay, from this point, so p dash q dash divided by r dash s dash from this figure now, from the diameter of the figure, p dash q dash divided by r dash s dash is equal to, we can take it as here r minus, it is equal to r minus y divided by r now. We are having here now from the similar triangles O, P, Q, O, R dash, S dash, we got PQ divided by R dash S dash is equal to P dash Q dash by R dash S dash is equal to R minus Y divided by R now. Because we have taken this distance is equal to R minus Y only. So here now adding just one here now, we are taking 1 minus of P dash Q dash divided by R dash S dash is equal to 1 minus R minus Y divided by R now. Now this equation can be modified as now, this equations now, we can write it now. R dash S dash is the common now, LCM. R dash S dash minus P dash Q dash, it should be equal to now R minus of R minus Y divided by R now. But R dash S dash is representing the neutral axis. Even though the beam is deflecting now, the length of the beam is always remains constant, and hence we can take it as now this is equal to PQ, R dash S dash is equal to PQ minus P dash Q dash divided by PQ, or in other words it is called change in length to its original length, or it is also called strain produced now, which is equal to epsilon. We can take it as now here R minus R plus Y divided by R now, or it is equal to Y by R now. R, that means strain is equal to, we can take it as Y by R now. So from this relationship we got now strain is equal to Y by R now. That is the strain produced within the beam is increases when the layer of the beam is considered far away from the neutral axis, or the layer distance increases from the neutral axis, the strain produced within that layer is also increases now. So bending stress, we are having equation now, strain is equal to, we can take it as strain is equal to, stress by strain is equal to, here it is equal to Young's modulus. From this relationship we got to here strain is equal to sigma divided by E now, or you can take sigma is equal to E into epsilon now, where E stand for the Young's modulus now. Sigma is equal to bending stress at a distance of Y from the neutral axis now. So from this relationship we got now sigma B is equal to bending stress is equal to strain multiplied by the elasticity, which is equal to epsilon multiplied by E now. Epsilon is equal to, already we determined its value is equal to Y by R into E, hence it can be taken as now E by R into Y now, or sigma B is equal to E by R into Y. Since E and R are the constants, therefore the stress at any point is directly proportional to the Y, that is the distance between the neutral axis to the layer considered. So the modified equation it can be written as now sigma by Y is equal to E by R now. Since the bending stress is inversely proportional to the radius now, therefore The maximum stress, the radius should be minimum and vice versa. Here, based on that relations, we are taking one problem here. A copper wire of 2 meters radius diameter, a copper wire of 2 mm diameter is required to be wound around a drum. Find the minimum radius of the drum. If the stress in the wire is not exceed to 80 megapascal, take modulus of velocity for the copper as 100 gigapascal. The given data in the problem is the diameter of the wire is given here 2 meter. The maximum bending stress is given sigma b, which is equal to 80 megapascal. It can be written as 80 Newton per mm square now. The modulus of velocity is equal to 100 gigapascal, which is equal to 100 into 10 to the power of 3 Newton per mm square now. The distance between the neutral axis of the wire and its extreme fiber, because here we required the maximum stress not exceed, that is the maximum stress is exceeded at the upper layer only from the neutral axis. So that is nothing but equal to the radius of the wire now. So y is equal to, we can take it as here radius, it is equal to diameter divided by 2, which is equal to 1 mm. The minimum radius of the drum is equal to, which is obtained now, r is equal to, because we are having sigma by y is equal to E by r now. From this relationship we got r is equal to, we can take it as E into y by sigma now. So from this relations now, we got E is equal to now, that is young small s is equal to 100 into 10 to the power of 3, we got y is equal to 1 divided by sigma is equal to 80 Newton per mm square. So just by using the relations, we got it is equal to 1.25 meters, that is the minimum radius that is required in order to induce a stress which is not exceed to 80 megapascal. Problem number 2. A steel wire of 5 mm diameter is bent into a circular shape of 5 meter radius. Determine the maximum stress induced in the wire. Take E is equal to 200 gigapascal. The diameter of wire is equal to given 5 mm. Radius of the circular shape capital R is equal to 5 meters. When we are converting into mm, 5 into 10 to the power of 3 mm. Modulus of velocity is equal to 200 gigapascal. That is 200 into gigapascal is equal to 10 to the power of 3 Newton per mm square now. The distance between the neutral axis of the wire and its extreme fiber, it is equal to y is equal to d by 2, which is equal to 5 by 2, is equal to 2.5 mm. The bending stress induced in the wire is equal to the maximum, it is equal to, by using the equations now, sigma by y is equal to E by r now. R sigma is equal to E by r into y required now. So from these relations now, E is equal to young small s is equal to 210 to the power of 3 is there, into y is equal to 2.5 divided by r is equal to here 5 into 10 to the power of 3 now. So by using this equation we got sigma b is equal to 100 megapascal or 100 Newton per mm square. Problem number 3 now. A metallic rod of 10 mm diameter is bent into a circular form of radius 6 meters. If the maximum bending stress developed in the rod is 125 megapascal, find the value of Young's modulus for the rod materials. The given data in the problem is the diameter of the rod is given 10 mm. The radius of bend is equal to given 6 meters. Just converting into mm, that is 6 into 10 to the power of 3 mm. The maximum bending stress is equal to here 125 megapascal. It is equal to 125 Newton per mm square now. The distance between the neutral axis of the rod to its extreme fiber is equal to the radius of the rod required, which is equal to y is equal to 10 by 2, it is equal to 5 mm. The Young's modulus for the rod metal is given by the relations. Here we have taken sigma b divided by y is equal to E by R. Now, from these relations now, E is equal to, we can take it as sigma into R divided by y now. So, by using these equations now, here now, sigma is equal to, we got to 125 Newton per mm square. R is equal to, here now, 6 meters, that is 6 into 10 to the power of 3. Here, divided by y is given now. So, y is equal to, here 5 mm now. So, substituting 125 divided by 5 into E is equal to 6 into 10 to the power of 3 now. By using the relations, he got to 150 into 10 to the power of 3 Newton per mm square, which is also equal to 150 gigapascal. Okay, this is nothing but giving the brief introductions. What is the theory of simple bending and the assumptions made, the relationship between the bending stress and radius of curvature and the Young's modulus. So, just we discussed a little, just 3 examples based on these relations. Okay, thank you.
Like, share and subscribe. Hit the bell icon for more updates.